I've had the pleasure of working with lots of wonderful students and collaborators, some of whom are here in this room. So I'm going to tell you about an analogy between statistical inference and statistical physics. And to me, these two fields, and more generally physics and computer science, have a great deal to say to each other. Statistical physics is the study of what behaviors emerge when many objects interact in some way. And the atoms in a gas or in a liquid or in a table. And statistical inference is, you can think of as what emerges when you have many variables of a problem, and these variables are interacting with each other in a way that depends on the data set that you're trying to analyze and your model for that data set. And then what emerges from that is a picture of how well the model fits that data and perhaps some predictions about the data. And I'll try to argue that those predictions emerge in very much the same way that physical predictions emerge about the behavior of a gas or a liquid. And in particular, so I want to, and you also want to, solve this problem of finding patterns in data which is noisy and incomplete. Well, data is plural, so data which are noisy and incomplete. And since all real data is noisy and incomplete. But there might be phase transitions or fundamental limits in our ability to solve this problem. So it may be that when the amount of noise in the data or how much of it is missing exceeds a certain threshold, we completely lose any ability to find patterns in the data. We might encounter a situation where we can do no better than chance, if there are such places, we should know about them. And then we want to both locate these transitions, but also find optimal algorithms that succeed all the way up to this point, algorithms that can extract as much information from the data as you possibly can. And as we'll see, sometimes there are different thresholds depending on whether you are thinking in terms of whether there is a sufficient amount of information in the data, or whether you're thinking in terms of efficient computation. There might even be zones where it is possible to extract information from the data, but it's exponentially hard in terms of the amount of computation you need. So we'll talk about that. Okay. So I want to start to explain this analogy with something that thousands of people do every day, and I want to figure out why they do it. So it always bothered me that when people had this, some data, they wanted to fit a straight line to it. It always bothered me a little bit that they minimized the sum of the squares of the error. Why do we do that? Of course, one reason we do that is that it's very easy to do. It's just a linear algebra problem. You can have MATLAB or Mathematica or 3 lines of code or whatever do it for you very easily. But why? Why is that the right thing to do? And when is it the right thing to do? So we have this model, y is ax plus b. It's a straight line. We want the best fit of that model to the data. And so why is this the best fit, the one which minimizes the sum of the squares? But why? All right, well, there are lots of justifications for this, and if some of you are actual statisticians, unlike me, then you probably have already come up with 3 answers to this question in your mind. But for me, the most concrete reason why this might be the right thing is that we actually have a model of where the data came from, and that model includes a noise term, that y is ax plus b plus w, where w is Gaussian, where w follows some normal distribution. And if that were the case, then the probability of the data given the model would be the product, if the data points were independent, and if they all had noise of the same variance, then the probability of getting the data would be the product of these probabilities, but these w's are the differences between the data and the model, and so we square those because of the Gaussian, and so we get, in the exponent, e to the minus this sum of squares. And so the most probable model, the maximum likelihood estimate, would be the one that minimizes the sum of squares. And this maximum likelihood estimate thing is, you know, I mean, I myself am kind of a moderate Bayesian, at least today. I don't really believe that scientific reasoning is Bayesian reasoning. I don't think that the main purpose of the brain is to update posteriors. But in certain contexts, I think that Bayesian reasoning is a good idea. So in this case, we want to compute this posterior distribution of the parameters of our model, the slope and the intercept, given the data. Well, if you have, as they say, a flat prior, so that roughly speaking, all values of these parameters are equally likely, this is proportional to the probability of the data given the model. And then the most probable setting of those variables is the one which minimizes least squares. Okay, this is one way to think about it. Now, let me describe this analogy with physics, and I've been promised that not all of you are physicists. Is that correct? Okay, thank God. Hang out with physicists for 2 weeks now. Okay, all right. So let's just do a change of variables. Let's say that the energy of the system, which I'll sort of explain in a moment, is minus the log of the probability. So then the energy is just that thing which was in the exponent, 1 over twice the variance times the sum of the squares. But if you remember your freshman physics, you know that this 1/2 kx squared here is the energy of a spring whose stiffness is k and which has been stretched by an amount x. So the stiffness is sort of 1 over the variance here. And then the energy is how much you would have to, the energy of all these springs if you had springs attaching the data to the straight line. In fact, my high school teacher showed us this once by taking a yardstick, or a meter stick. Are there meter sticks? So, and by attaching rubber bands between the stick and a bunch of thumbtacks, and it went boing, and okay, so there's the least squares fit. So then maximizing the probability is minimizing this thing I just called the energy, and that's what physicists call the ground state, the state which has minimum energy. We could ask, well, what if this energy function were different? So for instance, suppose you want to have a model which is more robust to outliers. So there are many sources of noise in the real world. Sometimes there's normal Gaussian noise, but sometimes you forgot to plug in the machine, or your rats have a cold that day, or one of the assistants bumped into the monitor and made the needle wiggle. And so sometimes there are these outliers. You know, sometimes you forgot to turn on the particle beam and so on. So now that spring is very stretched, and so it exerts a very strong force on the line, and that means that it will greatly skew our estimate. And so lots of people want some procedure for carrying about outliers a little bit less. Now there are lots of ways to do this. One way is what we've been warned many pollsters do during election season, which is they look at a poll and they say, that looks like an outlier, I will throw it away. But that's cheating and could lead to terrible problems. So another way to do it is to say, well, let's use a noise model which at large amounts of noise assigns larger probabilities than the Gaussian would. So it is more tolerant out here of large amounts of noise, which means that the spring force looks like this. So these, now the force is not quadratic in how, now it's not quadratic in how stretched the spring is. Instead, after a certain point, it becomes linear. So now the spring is like a piece of chewing gum that when you stretch it a lot, it gets sort of gooey and soft. And now these outliers don't pull on the stick as hard, and now the model doesn't care about them as much. So you can play with the energy. And playing with the energy means playing with the model, changing the assumptions of the model, including the noise assumptions. All right, good. So now let's put the Bayes hat on, because Bayesians would never say this is the right model. They would say, well, actually, there's this whole posterior distribution of models because you don't want just the right model. If anything, at the very least, you want some sense of how uncertain your estimate is, right? So the best thing, from a Bayesian point of view that you could possibly give is the entire posterior distribution. Well, since the probability is e to the minus the energy, there's this classic thing in statistical physics called the Boltzmann or Gibbs distribution, where the probability goes as e to the minus the energy. And in fact, this is the posterior distribution. So in physics, we have this additional parameter called temperature. And at very low temperature, this exponential is very sharp. It falls off very quickly, which means this probability is concentrated on the ground states. That doesn't mean the system can actually find them, by the way, just that if it could reach equilibrium, it would be concentrated there. If the temperature were very high, then all states would be equally likely. Good. So in this case, we can think of the temperature in a couple of different ways. If you remember, the variance of the noise was in the denominator of the exponents, so that was like the temperature. So higher temperature means bigger noise, looser springs, and therefore a less certain estimate. Now, of course, you could try to find these parameters from the data, but we can also just take them as fixed. So the picture here is that there is an energy landscape of models. In this case, our only two parameters are the slope and the intercept of the line. In that space, there is an energy function, which in this case is just a simple quadratic around the most likely value. And then the Boltzmann distribution, or the posterior, is defined somehow by this energy function. And it's the equilibrium distribution of the physical thing. So now the idea is you attach the meter stick with the rubber bands, but now you jiggle it a lot, and so it bounces around to some extent, and what you're interested in is that entire equilibrium distribution. Okay? Good. Did any of you learn anything from the past 5 minutes? Or was this analogy already completely familiar? Okay, all right, thank you. Okay, good. For a lot of people, this analogy is much less familiar than I thought it would be. So anyway, okay, good. So here's a classic physical model. It's called the Ising model or Ising model. It's a model of things like blocks of iron where you have atoms that can have little magnetic fields that are pointing up and down, and they like to be the same as their neighbors. That's the so-called ferromagnet. And when these interactions are strong enough, or equivalently when the temperature is low enough, then a lot of them line up together so that, for instance, 80% are pointing up and only 20% are pointing down, and that's when you have a real magnet. But Pierre Curie, who you may have heard of, he was married to Marie, found that there was an interesting phenomenon. As you heat up the block of iron, this magnetization, which you can think of as the fraction of atoms pointing in the same direction, you might imagine that as you heat it up, it slowly goes to zero as the system becomes noisier and noisier, but that's not what happens. Instead, there is a critical temperature, T sub C, which stands for critical or Curie, where the magnetization goes to zero. And so what happens is that below this temperature, you have a clear majority of atoms pointing in one way, with little islands of the minority. But above this temperature at large scales, it looks like white noise. And what's happened here is that above this point, the correlations between distant atoms decay exponentially with distance. And I want you to think of that as the system has lost the ability to convey, to transmit information over large scales. Okay, so now think of this as an inference problem. The system has lost the ability to relate the variables to each other over large scales. So what we're going to see are phase transitions in problems like this. So now the y-axis, instead of the magnetization, is some measure of accuracy. And the x-axis is some measure of noise, or perhaps how sparse the data is. So now imagine another problem, which lots of people want to solve. I have two clouds of points in high dimensions. I know I only have 2 dimensions here, but high dimensions. And maybe each cloud, give me a break. Let's say it's Gaussian. All right, we'll assume something about the noise. But there's enough noise, and the clouds are close enough together so that they overlap quite a lot. So now my goal is to label points according to which cluster they belong to. And so you can have these situations, a couple of us have a recent paper about this, where when there is enough information here, so for instance, if the noise is small enough, or the clusters are far enough away, or simply there are enough points, then there are algorithms which will label, for instance, 70% of the clusters correctly. Although interestingly, the algorithms you may have heard of, like PCA, are not necessarily the best ones. Then there will be a point beyond which there's nothing you can do. Asymptotically, you cannot label the points any better than chance. It's like flipping coins, no matter what algorithm you use. And in fact, up here, you can't even tell whether there are two clusters. In other words, you cannot distinguish this model, this type of data, from a null model where there is only one cluster. Okay? So you can't figure out what cluster each point is in. You can't even tell whether there are clusters. So that's the kind of phase transition that we're interested in. All right. So the other thing that I want to say is something that lots of people here work on, which are bumpy landscapes. So the least squares problem, the landscape was a simple quadratic bowl. In the Ising model, these are mountains from Santa Fe. In the Ising model, there are two bowls, one around the mostly up state and the other around the mostly down state. But in many problems we care about, the landscape looks more like this. So lots and lots of local optima. In other words, lots of ways to fit the model to the data that look pretty good, but that are far away from each other. So what to even do then? And this happens in so-called glassy systems, where you, for instance, have lots of variables, and depending on whether this constant is positive or negative, some pairs want to be the same, some pairs want to be different. So this gets into what computer scientists call NP hardness. So if you have all these local optima, how do you tell which one is the right one in some sense? Can you find it? Because even if you could tell whether it was the right one when I show it to you, finding it is hard in this kind of setting. So that was the introduction. Now let's explore these ideas using a particular problem that lots of people care about that has to do with social and biological networks. So here is a picture of this is from the early days of the blogosphere in the 2004 presidential election in the United States. Let's see, I guess the fourth to last. And sorry, of course, I'm very stressed today. And you should be too. All right, so here we have two groups of blogs, and these were labeled by some human who actually read them. I pity this person, but that labeled them as Democratic or Republican. And of course, as you know, humans have this annoying habit of only hanging out with people that are like themselves. So these blogs mostly connect to others in the same group, with only a few links between the two groups. So a fun pastime in network science is to take networks like this and then have some algorithm which divides it into its groups, and then you check that against what the human reader thought the two groups were. Here's another type of group structure. This is a food web from a lake that a friend of mine has studied. And at the bottom here, we have nutrients. These are plants. These are herbivores. These are carnivores. There's some cannibals up there. And you can imagine dividing this network in several different ways. So I just told you about what ecologists call the trophic level. But also, there are things that live near the surface of the lake. There are other things that live near the bottom of the lake or near the shore. So we could look for groupings of that kind. Here is a network of adjacent words in the novel David Copperfield. These are nouns, these are adjectives. The algorithm we used noticed that in English, adjectives usually come before nouns. We don't have this double before and after system you have in French, which is quite difficult for me. And adjectives are fairly often next to other adjectives, but nouns are not often next to other nouns, except in phrases like block model, which I'll show you in a moment. And then there was a third group here, which the algorithm used because there are words like light, which appear both as nouns and as adjectives in the text, so it was confused by those and it put it up there. Okay, so all of these are this community detection problem. So there's a model. Now, I should say that community detection, don't Google it, because you will get 10,000 papers. And many of them are quite ad hoc, and people argue endlessly about which algorithm is best, and they say, ha, mine got 82% modularity and yours only got 78%, ho. All right, so there's a lot of not so good work, and including some of mine. But I want to solve this problem in a mathematically principled way, okay? So I'm going to do that by adopting a specific generative model for the networks and then fitting that model to the network. Of course, I don't believe this model, okay? This is why I'm a moderate Bayesian. I don't believe this model is actually the right model at all. I just think it's like least squares. It's often quite useful and it's flexible. So here's the model. We have k kinds of nodes in the world. K might be 2 or 3. We can talk later, if we have time, about how to figure out what k is. That is a tricky question. But we'll assume that there are k kinds of nodes or k groups, and then there'll be some k by k matrix of how often they connect to each other. So here you would see this matrix entry off the diagonal would be large. This diagonal matrix entry would be low because those don't connect to each other at all. And so I don't know if you can see that subscript, but if a node I is of type R and a node J is of type S, then we'll say there's a link from I to J with probability P sub RS. So if you know about random graphs, you know about the Erdős-Rényi random graph model, that's simply where all of these P's are the same. And every pair of vertices is connected with probability P. Here, the probability depends on your types. Now, this problem to me is most interesting when the network is sparse. So intuitively, the fewer neighbors you have, the fewer friends you have, or even friends, the less I know about you. So the phase transitions are kind of easiest to see when these probabilities are order 1 over n, so that even in the limit of a large network, the average number of friends that Florent has is 6, say. Okay, so then there's a popular special case where there is a density Cn for connecting to others within your group, and typically a smaller density Cout for connecting to others outside your group. That's that kind of ferromagnetic or homophilic, or some people call it assortative behavior, like we had in the blogs. It's not the only kind of behavior we're interested in, but it's what we'll focus on today. By the way, I should mention that there are also a lot of networks, especially, for instance, technological networks, where you're more likely to connect to someone in a different group than yourself. So you shouldn't always think of communities as just dense internal connections. Okay, good. So let's do some math. So the probability of the graph given a set of types, or physicists would say a configuration for all these, or if you like a labeling, is easy to write down. According to the model, it's just the probability over all the edges of the product over all the edges of the probability they exist times the probabilities over all the non-edges of the probability that they don't exist. All right, so the nice thing about this model, it's a very simple generative model. Writing down the probability of the data, in this case the network, given a labeling, that's very easy. The challenge is flipping this around and getting the probability distribution of the labeling given the network. So again, using this analogy where the probability goes like e to the minus the energy, I'm going to assume here the temperature is 1. Then we just take the log and add a minus sign. We haven't really done anything yet besides changing these products into sums. But to physicists, this now has a very recognizable form. There is a generalization of the Ising model where, again, between every pair of vertices that are connected, between every pair of neighbors, there's some energy which depends on their states, just as in the Ising model, the energy of a pair depended on whether they were pointing in the same direction or not. A slight twist is that we also have connections between all the non-neighboring pairs. However, in the sparse limit where p is order 1/n, these terms are small because then this is close to log of 1, which is close to 0. On the other hand, there are a lot of them. We can't ignore them completely. But anyway, so it's an interesting model from a physics point of view, a generalized Ising model with connections between neighbors and weak connections between non-neighbors. Good. So what are the physics of this model like? What are its phase transitions? What does it do? So one thing you can do is look for ground states. So remember, ground states are the most likely state. So in the model where you're more likely to be connected to others within your group, the ground state would be the one with the fewest edges that cross between the two groups, okay? Because those are the higher energy edges. So here I've taken a network and I've divided it into two groups, and only 11% of the edges cross from one group to the other. Surely I have found communities. I will put this on the cover of Science or Nature and tell you that I have discovered that there are red nodes and blue nodes, and you will believe me. Because visualization, as you all know, is extremely seductive. So this is the ground state, but in this case it turns out there are lots of other ground states. There's another one. So here's another way to divide it into two groups with only 11% of the edges crossing between. But as you can see from the colors, it's completely uncorrelated from the previous one. So which one is right? Well, maybe neither of them are right, because actually, this experiment was inspired by a paper by Lenka and Stefan Böttcher. Actually, this network, I'm tricking you. It's a random 3 regular graphs. So everybody has exactly 3 neighbors, but then I wired them up to each other in a completely random way. And out of the roughly 2 to the n ways to divide it into two groups, there are some that look convincing, like this. Indeed, there are exponentially many, and they don't agree with each other at all. So what you're looking at is a bumpy landscape. In terms of energy, it has lots of local minima. In terms of probability, it has lots of local optima. And if you were to run some, say, gradient descent algorithm, which is basically what I did, but I did it several times, you'll think you're getting somewhere, but you're not really. You are overfitting. You're seeing structure which is not really there. And of course, as you all know, we are all very good at finding black cats in dark rooms, even when they're not there. We're good at that, and our algorithms are good at that too, if we're not careful. So the claim here is that people often treat these things as optimization problems. I don't think you should do that. Because even if you could find the optimum, which might be hard, what if there's another solution which is almost as good, but which is totally different? Okay? For one thing, your answer is not very robust. Imagine this mountain range. This peak is 31 meters high. 3,100 meters high. This peak is 3,102 meters high. Well, you know, okay, say you found that one and you happen to know that all of the others are a little bit lower. Is that the best one? But what does that even mean? Because all real data is noisy. And if I changed just a few of these edges, now this one would be 3,100 and that one would be 3,102. Okay? So focusing on this optimum, even if you could find it, which is hard, is very misleading. What you need to understand is the entire distribution. All right. I don't have my priest's collar on, but okay. Good. So here's a little slide about overfitting, which I'm happy to send you so you can use it on your students. So here's a set of stock market prices or poll results. And as you can see, we can fit this model really well with a high-order polynomial. And it's clear who's going to win the election today. But of course, you know that this is a bunch of hooey, and that what you should do is use a noisier model, right, so that totally fails. You'll actually get better predictions if you use a noisier model with fewer parameters, because your previous model was not fitting the underlying truth, it was fitting the noise. That's what it was reacting to. It was reacting to the noise and the randomness, and not the underlying pattern. Good, more slogans there. We want to understand the coin, not a particular sequence of coin flips. Okay, good. So let's now look at this block model. So I want to think about how much a link tells us informationally about a pair of nodes. So let me remind you, here are our parameters. C in and C out are the densities of edges within your group and between your two groups, and between two groups. There are k different groups. Your total average number of neighbors, your average degree, is, since each group has, let's say, an equal fraction of nodes in it, it works out to be this. So you have this many over k in your group on average, and this many total in the k-1 other groups. So I want to ask, if I were to tell you what type I is, or if I were to tell you a probability distribution of types for I, and then I tell you that I is connected to J, what do you believe about J? How would you compute the probability distribution of J given the existence of that link? Well, if you apply Bayes' rule, then you simply have to normalize this matrix so that it's stochastic, so that its columns sum to 1. And then it acts like a little transition matrix if you're into Markov random fields and something like that. And we can write this in a compact way. This is its second eigenvalue, lambda. And what we get is lambda times the identity matrix plus 1 minus lambda times this flat matrix where every entry is 1 over k. What does this mean? This means that with probability lambda, the type of J is the same as the type of I. The type just gets copied over by the link. And with the rest of the probability, the type of J is completely random, as if the link were not there. So this is a nice picture of this system because it tells us that lambda it's the probability that information is successfully transmitted across the link. It's some measure of the strength of the model, and you can see that it depends on how much bigger is C in than C out. How much more do you connect to others within your group than to the rest of the world? All right. So that's what I just said. Now imagine fixing lambda. So imagine fixing the strength of each link. For the physicists, we're fixing the coupling on the link. And now imagine increasing C, which is the average degree. So if every link gives me the same amount of information about you, and the number of friends you have goes from 10 to 20, well, that should make the problem easier, right? Because we're going to be able to infer more about you from your friends, because you have more of these links. Okay, good. So here's what we know so far. Some of this we know with a lowercase k. Some of it we know with a capital K. That's about, physics versus math. But we believe it all with a capital B. Okay, so here's the situation for two groups of equal size. And it looks very much like the Ising model. And so basically, when C is big enough, turns out what matters is C times lambda squared. That's a little surprising at first, but it makes sense. When it's big enough, we are in an easy regime. So not only can you find the communities, by which I mean you can label the vertices better than chance. This is a measure of accuracy here. So you can get 90% of the vertices right, say. Not only can you do that, but you can do it easily and quickly so that there are efficient algorithms that do it, spectral algorithms, belief propagation, which I'll tell you about in a moment, and so on. But below that point, it's impossible, no matter how much time you have. And I didn't believe this at first, but indeed, no matter what you do in this regime, you cannot asymptotically do any better than flipping coins. And the reason is that if you think of this whole process as like an information theorist would call it a noisy channel, nature knows what group the nodes belong to. and nature is trying to tell you. But the way nature does this, for some reason, is by generating a network according to this model and then showing you that network. In this regime, this way of communicating is simply too noisy to get very much of the information across. And this can be proved. So when there are more groups, it turns out, you might think 2 groups, 3 groups, who cares? This, well, it turns out that when there are more groups, some genuinely new phenomena appear. There is still an easy regime up here. In fact, the threshold is the same as it was before. There is still an impossible regime down here. But in between, there is a very interesting place where we know that if you are given enough time and you are given the ability to compute or to sample from the entire posterior distribution, you could succeed. But we think that it takes you exponential time to do so. So we think that in this regime, it's information theoretically possible, but computationally exponentially hard. Now, of course, we cannot prove that it's exponentially hard without resolving major open questions in computer science, like the P versus NP problem, but we could hope to prove concrete statements about specific algorithms. So this possible but hard regime is very interesting, and I should emphasize that all of this is very familiar to the physicists who study spin glasses. So they've seen phase diagrams like this before, but it's very nice. It gives our field new life that it shows up here in inference. Okay. Oh, and by the way, here is this regime where I had my red-blue picture, where there are clusters of good-looking states, but you can't even tell, if you think about it harder, these clusters are no more convincing than they would be if there were no structure there at all, if the graph were simply a simple random graph. All right. By the way, you get the same thing in high-dimensional clustering. This isn't just a phenomenon about community detection in networks. So suppose that you have m points in n dimensions, and let's suppose that m over n is some constant. So our data is high-dimensional and sparse. It's like saying, so n is the number of different genes I'm going to measure, their activation, and m is the number of different rats I have in my laboratory, and n is 10,000 and m is only 100. So I have a small number of points in a very high-dimensional space, which would already make you worry that maybe we're going to overfit. And then we'll have k clusters. We'll make the noise Gaussian for mathematical pleasantness. And then we can ask, can we find the centers of the clusters? Can we label the points? Can we even tell that there are clusters and that it's not just a fiction that we think we're seeing? And indeed, there are phase transitions here as well, and also a gap where the standard algorithms like principal component analysis are not optimal, and where it's information theoretically possible, but we think it's hard. Okay, so in my remaining time, I want to show you a little bit more of the mathematics and the algorithms. So how many of you are already familiar with belief propagation? Okay, good. I myself tried to learn belief propagation several times. What always happened was that there were double superscripts and double subscripts, and it made my head hurt so much that I decided to read the news instead. So I've tried to keep it down to single superscripts and subscripts. I might have failed once or twice, but the idea is very simple. So now I should preface this by saying, you're probably thinking, well, he says we should look at the entire Gibbs distribution or Boltzmann distribution. Why don't we just sample from it using Monte Carlo? Well, you could do that, but in my experience, this is too slow, precisely because we have this bumpy landscape. Monte Carlo tends to get stuck in one place for a long time, and to take a long time to get over these energy barriers and explore the other valleys in the landscape. So I would argue it's too slow. So belief propagation is different. It tries to estimate the probabilities directly that, for instance, node I belongs to group 3. So those are the marginal probabilities. So each node has a marginal distribution of what groups it belongs to. And belief propagation tries to figure these out in the following way. Each node sends its neighbors an estimate of its marginals, and they do a little calculation and then send back out new estimates based on the estimates they received from their neighbors on the previous step. But there is a twist, which is that when I talks to J, I only pays attention to what I received from its other neighbors, K, and not what J said to it. Now, why is this a good idea? Well, there are deep reasons in terms of variational methods, but another argument is that if I go on a talk show, and there's another guest on the talk show who's also a scientist, and I say, I'm a scientist, and lots of us scientists think that global warming is just a hoax. And then the other guest says, you know, I just heard from a scientist that global warming is just a hoax. And then I say, I just heard it from another scientist. And then she says, I just heard it from another scientist. Then obviously this would be a pointless echo chamber where this information is just being amplified between the two of us. Of course, no talk show would actually be like this, especially in the United States. People would work very hard. The host would say, wait, let's bring in some fresh information from the rest of the world. So that's how belief propagation works. Okay, so we're going to update these probabilities until they reach a fixed point. Well, they might never reach a fixed point. Or they might reach a bad fixed point. Or it might take them a long time. But when it works, it's pretty fast, and often it works well. So when does that happen? So first of all, oh, and by the way, in addition to the marginals, it returns something called the beta free energy, named after Hans Bethe, and which is a kind of estimate of the free energy, which is also a measure of how, I would call it a measure of how well the model fits the data overall. Okay, so how do we update these beliefs? It's really easy. And you know, it's still before lunchtime, so don't tell me you're too tired to read this equation. So I'll lead you through it. I guess, right, and no double subscripts. Okay, good. So this is what I says to J about the probability that I belongs to group S. This is just a normalization. If you want there to be a prior probability that I belongs to group S, maybe you think most people belong to group S, you can put that there. Okay? Now, we take a product over all our other neighbors, the ones other than the one we're talking to, of the messages that they are sending us about the probability that they belong to some group R, but we weight these messages by the probability that there would be a link between us if indeed they were in group R and we were in group S. This is just Bayes' rule. That's all this is. This is just saying that, well, if I take your word for it that you're in group R, since there is a link between us, that updates my probability that I am in group S. And I do these updates for all my neighbors, and that's this product. And this is this other effect, this weaker effect from the non-neighbors. Don't worry about that. So belief propagation is just Bayes' rule, but with this clever twist that when I talk to you, I use the data, the estimates I've received from everybody else. Good. Now you can code it up. It's a pain in the ass with the data structures, but now you can code it up. You know the whole idea. All right. But there's a huge assumption we made here. By taking this product over all our neighbors, we assumed that they're independent of each other. Or specifically, that they are correlated only because they're both correlated with us. And this is exact only on trees, where indeed their interactions do go through us. Well, in a real network, there would be some loop which connects them. Well, if that loop is long and the correlations decay, then asymptotically they'll still be independent. Well, but real networks have lots of triangles. People introduce their friends to each other. Well, yeah, you're right. They're not independent. This is just wrong. But in practice, it's often not too badly wrong. And it's really fast. So, in fact, we know relatively little rigorously about the effect of short loops. But we do have theorems about what happens when things are locally tree-like, which is at least the case for these synthetic networks. So there are lots of caveats here, and there should be. Okay, anyway, good. This is fast because the amount of time it takes to update each step is only proportional to the number of edges. So linear, if you like, in the size of the data. And it's competitive with a lot of other people's algorithms. So here's that phase transition before. It's parameterized in a slightly different way. Now this is the probability, the ratio of connecting outside your group to inside your group. So this is a completely random graph, equally likely to be connected to everybody. This is you only connect to those in your group, which would make this problem pretty easy. And here is the accuracy achieved by belief propagation. And here is this impossible or undetectable regime where no algorithm can succeed. So at first you might say, well, why should I believe that if belief propagation fails, that nothing can succeed? It's just one algorithm. Well, but at least for these synthetic networks, it turns out to be provably optimal in many ways. And there's been lots of recent progress on that, including made by some people in the room. So there's this threshold here for two groups, and let me just explain why. Why does belief propagation have trouble? So there is a stupid fixed point that belief propagation could fall into. So if you tell me, if all of my friends tell me, oh, I'm equally likely to vote for Clinton or Trump, then I sit there and say, well, I guess I'm also equally likely to vote for Clinton or Trump. So this point where all the marginals are uniform, everybody is equally likely to be in every group, it is a fixed point of the equations. It's not a very helpful one because it's like flipping coins on everybody. So the question is this fixed point stable or unstable? So for two groups in this regime, it becomes stable, and in fact, it seems to become globally stable, so that no matter how you initialize belief propagation, you'll fall into it, at least if you initialize things with some randomness. And then you'll do no better than a coin flip. So we conjectured this in a physics paper, and then very quickly it was proved by some clever mathematicians. And I just want to mention here that unless I already told this joke in this room, all these talks are blurring together, so I can't tell about proving things or not proving things. So I like to prove things when I can. So I love proving theorems. And if I can, then I publish in the mathematics and computer science literature. If I can't, then I have my students do some beautiful experiments and we publish in the physics literature, and I get to publish either way. It's great. I encourage this as a career strategy. Okay, good. So then here is this situation when we have more groups. So here's the easy regime where you get a high accuracy no matter what. Here's the impossible regime where you get a low accuracy no matter what. But here's this interesting regime where if I start out close to the truth, well, I get a high accuracy. But why would I start out close to the truth? Well, if I was really lucky, or if you gave me a big hint, or if I had some additional information about the nodes that told me, for instance, the correct types of 20% of them. But if I start out without that information, I fall into the stupid fixed point and do no better than chance. So in this case, belief propagation has at least two fixed points. In fact, it has more. But the accurate one seems to have a very small basin of attraction. So that, for instance, Monte Carlo methods would take exponential time to find it. Belief propagation will only find it if you start out very close to it in an exponentially small fraction of the space, and otherwise you fail and find the trivial fixed point. What I just said is a conjecture and could be proved. So that is a concrete statement which we should try to prove. Okay. Good. But we do know in here that it's information theoretically possible. We know essentially where that threshold is, for instance. All right, so in my remaining time, I just want to show you some variations on this theme. So I just mentioned, well, what if you know the correct labels of some of the nodes? Well, obviously that will help. So this gives us another parameter in addition to the parameter of the block model. Let's say that you know a fraction alpha of the nodes for free. You have metadata about them, for instance. So the question is, when can you propagate that information to the rest of the graph? Of course, you'll always get those correct because I just told you them. You'll do well on their neighbors, maybe their neighbors' neighbors, but when will the information percolate out and really help you do well in the entire graph? Well, here's the accuracy, and here you see this line of discontinuities where if I give you more information, the accuracy suddenly jumps. So this is another physics paper, and so you can get discontinuities in the amount of information you have initially. So you can see we can play this game in a lot of different models. What about dynamic networks? Networks change over time. So let's say that at some rate, I change what group I belong to. People do occasionally change their minds, although not nearly often enough. So then we can write down a phase diagram where one axis is how much you persist in not changing your mind and how strong or weak the block model is. And then we get a nice curve there, which tells you, on this side, you can do a good job of labeling the points at all times. On this side, you can do nothing at all. What if we don't know how much structure there is? So in everything I've assumed, I have not been doing what people call parameter learning. I've been assuming that for some reason we know the correct parameters of the block model. Well, but this is exactly why we overfit sometimes. What if we think there's more structure than there really is? Then we are in danger of finding structure that isn't really there. Okay? So physically, that's like setting the temperature too low. It's being too greedy. And it's focusing too much on the high probability states. It's giving them more probability than they actually have in the posterior distribution. Does that make sense? If you remember the form of the Boltzmann distribution, no chalk, never mind. You have e to the minus energy divided by the temperature. So if you lower, it's okay. If you lower the temperature, you're emphasizing those low energy, high probability states more than they deserve. So here is a nice phase diagram from Pan Zhang and me. Pan was here as a postdoc and is now in Beijing. He was at Santa Fe in between. So here's the true structure, the amount of true structure in the model. Here's the amount that we assume. Here's where things go well. So red means we succeed in labeling things accurately. If we set the temperature too high and we don't assume much structure, we underfit. We don't see structure which is really there. But if we set the temperature too low, we can overfit. We enter this stands for spin glass. We enter this glassy state, and that's where we have that kind of situation where there are lots of good-looking fits, but they're all just illusions. But how can you tell where you are in this diagram? How can you select the model? How can you tell, is this a random graph, or is it a graph generated by the block model? Well, the physicsy way to do this is to measure the free energy. So let theta stand for all the parameters that we're trying to figure out. The strength, the probabilities of connecting inside and outside your group, and so on. So the best overall model, I would argue, is the one that has the largest total probability of generating your data when you sum over all the things that you're trying to learn. And some people call this the evidence. I think that's a terrible word. I don't know why they do that. But this is what a physicist would call the partition function. And maximizing this means minimizing minus its logarithm, and that's the free energy. And if you remember your thermodynamics class, you know that the free energy has two terms. There's the average energy, which here is the average of the log of the probability. So if you want high probability, you want that to be small. But there's also this entropy term. S is the entropy, which is roughly the log of the number of good ways to fit the model to the data. So minimizing the free energy means finding a model with many good solutions. That's kind of interesting, that it can fit the data robustly rather than in a single fragile way. So I think that's an interesting philosophy of how to do this model selection. And in some cases, this is really what you would do as a Bayesian if I told you these two models are equally likely, which one do you prefer? But that means we can tell whether the structure is statistically significant. In other words, can we really distinguish the data from a null model with no structure at all, such as a purely random graph? So here's something that we did to the blog network, Pan and I. We're interested in hierarchical structure, communities and subcommunities and sub-subcommunities, but we stopped dividing it when this free energy criterion told us there are no real communities anymore at this scale. So you've divided it down to something that looks like a random graph. And this seems to work quite well, and it's fast, and I like to believe that it divides, for instance, the Democrats into the labor Democrats, the reproductive rights Democrats, the environmental Democrats, and the Republicans into the actual capitalists and the theocrats and so on. I'm very sad to say, though, that all of the brilliant thoughts that were recorded in these blogs seem to have been lost in the mists of time. So very sadly, we can't go back and read what all these people were saying and confirm this picture. I'm sure that it was very thoughtful and brilliant and incisive, but anyway. So you don't want to, again, the slogan is we don't want to maximize things. We want to look for a robust fit. Another way to put this is we would rather have the consensus of many good fits than the single best one, even if we could find that single best one. All right, I have a bunch of other things to say, but it's 1 o'clock. I will say that there's some beautiful stuff about spectral clustering, which you can get from something called the non-backtracking operator, where again, there was this fun interaction where Lenka, Florent, and I and some other people conjectured a bunch of this stuff, and then Mark and Mark Lalarge in the back of the room and some other people proved it. It's very handy when this happens. And the way we derived this spectral clustering algorithm is by thinking about the derivatives of belief propagation, and there's its spectrum in the complex plane, and it looks like a scary pumpkin. I know we just had Halloween, or the Eye of Sauron. Okay. And all the regular spectral methods fail, fail, fail away from the transition, and this one comes right down to the transition, yay. Okay, good. So let me conclude. So, there's a lot of interesting cultural differences between disciplines. So I've tried to argue that a lot of problems in statistical inference that involve sparse and noisy data have these phase transitions beyond which no algorithm can succeed, and that sometimes ideas from physics can help us invent and analyze algorithms that are optimal, that succeed all the way up to that point. Much of this work can be made mathematically rigorous, which we should do. But there's a thing here. So I have a mixed relationship with the machine learning community. So I've published there a couple of times. But when I look a lot at those papers, they say, well, last year on our 6 favorite benchmarks, we got 73% accuracy. But our algorithm now uses a Golubitsky-Solovechkov approach to stochastic gradient descent, and instead of flathead screws, we use Phillips head screws, and we used a new kind of motor oil, and we kicked it 3 times and walked around it twice counterclockwise before starting the machine, and now it got 78% accuracy. So no offense, but this is how a lot of papers in machine learning read. And of course, achieving the highest accuracy we can is an important thing to do. I'm glad that Siri understands me, although, she has even more trouble with my French than you do. But for me, coming from physics, there's this other culture, which is that you want models which are simple enough to be tractable while being just complicated enough to capture, at least qualitatively, the phenomena that we care about. And we want simple algorithms, not really fancy ones, because simple ones we can understand something analytically and understand something mathematically about their strengths and weaknesses. if you have a really fancy algorithm, it might be better than mine, but why? And on which data sets? And how does it do it? What's going on? I don't know. Okay, so that's where I'm coming from. And I'll just end with this slide, which you might enjoy as a rejoinder. You're trying to predict the behavior of insert system here. We'll just model it as a simple object and then add some secondary terms, easy, right? Why does your field need a whole journal of its own? So there's nothing more obnoxious than a physicist first encountering a new subject. All right, thank you very much.
Hi. It seems to me that you are assuming Gibbs-Boltzmann distribution all the time, right? You have this free energy, and how do you set the temperature? Is it something that you self-consistently determine? And why not actually looking for some self-consistent determination of the full distribution function? Not Gibbs-Boltzmann, but something else.
Well, let's see. So, I mean, in a trivial sense, the Gibbs distribution is the posterior if the energy is simply minus the log of the probability of the data and the parameters, right? So in that case, the temperature would be 1, and then varying the temperature would be like varying, well, there's often a change of variables. So for instance, you can exchange that parameter lambda, which is how strong the block model is, how strong the community structure is. You can exchange that for the temperature if you like. Just as in the least squares example, you could take the variance of the noise and call it the temperature, right? So indeed, in the paper, in this paper I showed you before with this phase diagram, we do try to find the temperature. So we, by minimizing the free energy and also looking for when belief propagation converges at all, we try to figure out, we try to end up on this diagonal line. And so you can do that. You can do parameter learning with expectation maximization algorithms, which in physical terms are trying to minimize the free energy. So they're doing some kind of descent in the free energy landscape of possible models. So I guess two answers to your question. If you know the true parameters and you put them into the energy function, then in a trivial sense, the temperature is 1. If you don't know the true parameters, then one way to think about varying them is to think about varying the temperature. But sometimes, the temperature is just one parameter, so sometimes you want to vary multiple things independently.
There might be more complex things. Temperature, chemical potential that you didn't think about, non-equilibrium distribution.
Well, it's also true that I'm only thinking about equilibrium, yes. And in fact, in this regime where we think that it is possible but exponentially hard, physically what's going on is that if this is the energy landscape, so remember lower energy is good, the accurate fixed point is here, but it has this narrow basin of attraction. So if I do, and there's this energy barrier, here's the trivial fixed point, and there's an energy barrier in between them. So if I start almost anywhere and do descent, I'll go there. If I do Monte Carlo and move around, it will take me exponential time to get over this barrier and find the accurate fixed point. At the same time, if you have exponential time and you have the luxury of doing exhaustive search, then you can find both these fixed points. And then you compare their free energies, and then you say, oh yes, I prefer this one. Okay. So that's the physical picture of the hard but possible regime. Yeah, so there the problem is that finding the equilibrium is very hard, right? Precisely because of this barrier. By the way, I just want to say one thing before. So a lot of people like to convexify things, right? But I think convexifying here is a bad idea because you would be throwing away this information that there really are multiple minima, multiple optima. And if you did convexify it, I'm really not sure what would happen to the function. but I think there's some danger that you would end up making it look like that or something. And then this information would completely disappear. So, yeah, yes.
Yeah, I really enjoyed your talk. I think this was very clear, and I really liked the analogy with StatMech.
Well, thank you.
I mean, yeah, so of course, if I say something nice, is to say something a bit more controversial behind. Yeah. No, so last time we heard about how can we cure cancer, and the main example you gave is how to categorize blogs about political election. So these are like two ends of the spectrum of interesting questions. Yes. And I think, okay, I think of course all you did is much more relevant to many more questions. So I was wondering whether you could say a few words about what this kind of method could be applied to other than political blogs.
Yeah, well, can you repeat the question? The question is, labeling blogs is much less important than curing cancer at one, right? Which is true. It's especially less important when we already know the true labels of the blogs and we're just asking how well we did. But so, okay. I have mixed feelings about the field of networks. I think that it is a good field, but I think it is too popular for its own good. And I have seen a lot of people take rich, interesting data sets with all sorts of attributes on the data, and then they put them through a meat grinder, and on the other side, a network comes out, a graph. So they threshold things so that each pair of nodes is either connected or not, and they threw out 90% of the data they had. And they seem to do this because then there's some nice software package for doing things like community detection and to give you nice visualizations of the network. And I think this is unfortunate. So I think that if you have a type of data set, you should think about all these issues in a way which is indigenous to that kind of data set and not convert it into a network. So that's one thing I wanted to say. So the network example is, it's popular, it's pretty, it's easy to visualize. But like I said, many of these same phenomena also appear for clustering high-dimensional data, or for doing regression in high-dimensional data, or in doing compressed sensing and sparse recovery, which is something that people here have worked on a great deal, where you are trying to get a sparse signal from noisy samples and not very many samples. And that's related to medical imaging, MRIs, to astronomical imaging, to many other things. So I also think that people in genomics are not thinking hard enough about whether they might be overfitting. And I think that this is one of the mechanisms, not the only mechanism, behind this crisis of reproducibility in genomics and biomedicine. Of course, you know, there are many other mechanisms, publication bias and so on. But I think one of it is that people are not thinking clearly enough about how statistics changes in sparse, high-dimensional regimes, because that's not what classical statistics was built for. It was built for dense data in low dimensions. And so I've seen people take tools off the shelf, like the Ake-Ike information criterion, the AIC, one of these three-letter things. And they use that on something like a network or something like high-dimensional clustering to tell whether something is statistically significant or not. And it's just wrong. It was built for normal distributions. It was, you know, it's just wrong in that context. So culturally, part of what I'm trying to get across is that there are interesting new mathematical questions about how to judge statistical significance whenever your data is sparse and noisy and high-dimensional. And there are lots of interesting open questions, but the standard tools of statistics, I would argue, are, you know, not sufficient. Does that at all answer your question? Yes, okay, great.
Yeah, hi. So
Hi.
I was wondering that, for example, there is a paper by Herbert Simon about the architecture of complexity, where he exactly says that any kind of complex system is going to have some hierarchies, like the hierarchical clustering that you were showing. So even for natural images, for example, so these probability distributions, if we want to model them, one might have the impression that we have to include this hierarchical structure in the model of the probability distribution of the posteriors. So I was wondering if you have any insights from statistical physics to do that.
No, that's a great question. And it's true that the block model I described has a single level of organization, just these k different groups. So people have invented a bunch of different hierarchical versions of the block model. The process of fitting them to a network is now trickier, right? Because it's a more complicated model. What we did in here was a kind of hack where we used the block model to divide it into groups, and then we used the same one-level block model to divide each group into groups. This is not perfect by any means. So probably the best way to answer your question is that there are many ways to make the block model more elaborate. Okay, so for instance, you can deal with the fact that some people are simply more popular than others. So you can give each vertex an expected degree and just say, well, they're in the same group, but this one has more friends than that one does. That's called the degree-corrected block model. And there are lots of results about it on both the physics and math side. There are hierarchical versions like you described. Aaron Clauset and Mark Newman and I have one version of this where we fit a kind of tree. Tiago Peixoto has another version where he has a sort of block model of block models. So yes, by all means. I think these might work better in some contexts. They are also harder to analyze. And they might also be harder to fit to the data unless you start using clever stochastic gradient descent with Phillips head screwdrivers, which is good. If you have data in front of you, you should do whatever works. As a theoretician, it might be harder for me to say something about.
Thank you, Chris. So I think we can stop here.